Greetings, this is Dr. Benjamin Prather, and I'm here to present my Cobordism model of space-time and perhaps all of physics. And I've put together a PDF file outlining my ideas, so hopefully I can switch to that pretty seamlessly. And this is what I would like to present today. So, in my Cobordism model of space-time, well, first of all, on YouTube, I go by UtesFan100, go Utes. But in 2012, I participated in CosmoQuest's Against the Mainstream to present my idea of the refractive field theory of gravity. And basically, this is my modern incarnation of those ideas. I've learned a lot since then. But my interest in posting about this idea has been reinvigorated by discussions I have seen on Chantal Ross, The Mechanical Universe, the discussions that she had been having with James Elias on his channel Inductica, and also on her channel Red Pill 6313. The mathematics in this is largely influenced by the book by Aldrovandi and Piera. Probably butchered that horribly. I'm sorry, I apologize. Their book Teleparallel Gravity, which that discussion at CosmoQuest led me to re-envision my thoughts on the idea and formulate them and then research. And I discovered their book and realized that a lot of the mathematics in their book is probably what I was thinking. I just have a different philosophical take on what they mean. The mathematics from what they present in the book and the mathematics of what I plan to describe here is largely identical. Okay. So let's look at the measurement frame. So whenever we make measurements, we're doing this relative to some kind of reference frame. And when we're dealing with general relativity, we're oftentimes dealing with large scale things. And any of our reference frames, we can basically use a boost or rotation to get to that reference frame, to any other lab frame that we might be using. But the International Celestial Reference Frame is based on quasar locations, and it can be used to calculate positions within centimeters if you're in near Earth orbit, or within a meter or so at solar system scales. So that shows that the solar system has ridiculously large length scales compared to a meter. So that shows that the precision of flatness, our solar system is very flat. And in fact, we can expand this idea of flatness by looking at the density of galaxies at various distances, and we can measure the distances pretty accurately by there are standard celestial objects that have a specific brightness that we can measure to determine the distance. And then we look at how many galaxies there are at the distance, and we find that if we assume that the universe is uniform, we would expect a uniform distribution of galaxies. And if we assume that galaxies are distributed uniformly, that confirms, we can use that to measure the flatness or curvature of the universe. That would appear as variations in the galaxy densities, and we don't see any. So that shows that even at the scale of clusters of galaxies and beyond, the universe still appears to be very flat. So once we have our coordinates for space, we have 3 coordinates. Although the International Celestial Reference Frame is spherical, we can transform that into Euclidean coordinates. So that gives us 3 spatial coordinates that are flat. What about our time-like measurement? Well, we're very biased to the speed of time near the Earth's sea level. So that is basically the measurement that we use everywhere in the universe, wherever we can observe. We have observed that clocks run slower in satellites near Mercury than they do on Earth due to the gravitational time dilation. And a satellite out as far away as Jupiter, but perhaps not too near Jupiter, will be in a gravitational field lower than what we have, so their clocks would run a little bit faster. And we would just calibrate our clocks so that they're adjusted to match what we see here at Earth sea level. And then that is the time component that we basically would calibrate any clock to, and for any measurements that we make. So that gives us a very flat 4-dimensional reference frame to measure against. And any lab frame is basically just a boost or a rotation to that frame. Although usually we define them locally anyways. That's a whole other rabbit trail I don't want to get into right now. The CMBR dipole anisotropy does seem to give us a preferred reference frame. So basically, that is a reference frame that we would be moving relative to. Although the expansion of the universe itself, there is a direction where that expansion would be isotropic, and then a time-like direction orthogonal to that. And the idea that a lot of people have is that CMBR dipole anisotropy corresponds to that reference frame where the expansion of the universe would be isotropic. All right, so I'm describing a Cobordism model of space-time. Maybe we should take some time discussing space-time and Cobordism in general. So we've already talked a little bit about space, but if I have a region of space, I can model that region as a 3-manifold, perhaps with some kind of boundary. If space flows, then that, and I might not be thinking about, I'm actually thinking about in ether, not the actual space, because space I'm going to think of as being our coordinate frame that we have that's independent of any physics, and then the space in ether is what is the space that actually physics are playing out in. Those are two different concepts. So the space that our physics are playing out in is a 3-manifold that relative to our coordinate system could be flowing at each point. So if I've got an initial configuration of space and a final configuration of space, and I've got all these little trajectory lines going from one to the other, that's basically the structure that defines a cobordism. So the formal definition of a cobordism is a manifold whose boundary is 2 manifolds, 1 dimension less. So in this case, the boundary would be 2 3-manifolds. So it's going to be a 4-manifold. And then basically, we can arrange it, twist it around, so that the one manifold is at one layer, the other manifold is at the other, and all the other stuff going on in the manifold is in between those. And then we can put a unit length on that distance between them, and that's going to parameterize all the slices in between our initial configuration and our final configuration. That in a cobordism is called a Morse parameter. But in our space-time model, that Morse parameter is time. So the manifold at each Morse parameter represents a slice of the flow of the manifold. So space and time have the structure of a cobordism between 3 manifolds. Now if we go back all the way to the Big Bang Theory, that initial 3-manifold is actually just a single point that the Big Bang sprang from. One of the things that a cobordism has is, well, in a cobordism, the topology of the manifold does not need to be the same. It can change with the Morse parameter. And the times where these changes happen are called critical points of the Morse parameter. And then the points where they happen in the ether at that point, at that time, are called the critical points. So the idea is particles could represent the holes, because you can have holes in our 3-manifold, as long as the boundary of the hole is not in our manifold. That is fine. And the interactions would be singular points of the Morse function. So that is literally where 2 holes come together, and then they can change their topology, and then we have 2 holes with a different topology. That is what interactions are. Another type of hole we can have are black holes. So the idea is, for a black hole, you get to a point where the deformation is so much at the event horizon, our physics stop working. And in this model, that basically would be just another type of hole in our ether, and the boundary, the event horizon, would not be in our manifold at that point. Once the singularity forms and we get the event horizon, that region of space is no longer in our manifold. We just have a hole that is the black hole. And actually, it's the neighborhood outside the event horizon, because the manifold, the three manifold itself, cannot have any boundaries. And if you cut a closed manifold out of a manifold, you get an open set, so there are no boundaries. Okay, so the next thing I want to talk about are Noether currents. Noether currents, my apologies for mispronouncing. But the main idea here is we can actually correlate the symmetries of a system, which a mathematician like myself would call a geometry of our space-time, with the, if we have dynamics in that space-time, then that is going to have preserved quantities of that dynamics that we call Noether currents. So in the context of a space-time, translational symmetries, so if our space-time is the same over here at this space as it is over at this space, that corresponds to conservation of momentum. And if it's the same temporal symmetries, if it's the same today, tomorrow, and next week, that corresponds to conservation of energy. For some reason, I'm thinking of sugar cubes right now. Anyways, rotational symmetries correspond to the conservation of angular momentum. Boost symmetries correspond to conservation of the center of mass frame. So, I do want to mention we're living in an expanding universe. So if our universe is expanding, that breaks the temporal symmetry. So if our space is expanding, then as time goes on, the space is that means if our space is expanding, we no longer have temporal symmetries. So we no longer have conservation of energy. And that is why, as light is traversing across the universe, it is redshifted, it is losing energy. Why does that not violate conservation of energy? And that is because time symmetry is being violated by the expansion of the universe, and that is what accounts for that energy loss. Also, if we believe the CMBR reference frame is a preferred reference frame, then boost symmetries no longer apply. And in fact, that CMBR reference frame, the dipole anisotropy would cause a drag on whatever system we're dealing with, and then that drag would cause the system to slow down to where it is no longer moving relative to the CMBR reference frame on ridiculously long time scales. But that CMBR breaking of boost symmetries, that then produces a force on isolated systems that causes them to come to rest relative to that preferred frame. All right, so with that, we can look at the symmetries that we observe in our space-time to determine what the local symmetry or geometry of our space-time is. And when we consider boosts, we need to consider how is the velocity direction dependent on the velocity of the boost. Our mental conception suggests that these times should be independent of a boost. So our time direction should not change. And if that's true, then we'd be in a Galilean space-time, and energy would be a preserved quantity on its own right. If, when I boost in the x direction, time boosts opposite the x direction by some scaled amount, then space-time is Euclidean, and time is just an extra space-like dimension that's somehow stretched. And then there would be some value c that corresponds to that stretching, and then energy squared plus the scaled momentum would be a preserved quantity, because basically time would just be a rotation of space, so momentum would just be a rotation of energy in the space, would be like the time-like component of momentum. And then we can rotate this around freely. So we definitely don't seem to live in a space-time like that. We can't rotate time so it goes backwards. We can't rotate x so that way going to the left is back in time. Anyways, If time changes in the direction of the boost, if our time vector moves in the same direction as the boost, then that corresponds to a hyperbolic rotation, which is the fundamental mathematics rather, of the Minkowskian spacetime. And there, the energy squared minus the momentum squared is preserved, where c is a parameter corresponding length and time. There are two main observations that show that the Cobordism that we find ourselves in is Minkowskian. One is we can actually measure which of these three we're in by looking at if we have circular acceleration, as we increase that acceleration, how does that change with speed? In the low speed limit, it's going to grow quadratically, like a parabola, proportional to velocity squared. However, in these other two forms, it's going to deviate from that. If it's Galilean, it will stay that forever. If we're in Euclidean or Minkowskian, if we're in Euclidean, it will slowly decrease from that. And if we're Minkowskian, it will increase, and then asymptotically, it will have an infinity when that speed gets to c. It will take an infinite amount of force at that speed of c. For the Euclidean, it actually goes to 0 force at that speed of c. But in particle accelerators, even when dealing with atoms and particle accelerators, because we can accelerate those to high enough speeds that we can measure this effect, and we see that all the measurements are consistent with an asymptote near the speed of light. Another prediction is that this preserved quantity allows us to convert, this is called the rest mass of whatever it is we're talking about, and we can convert the rest mass into energy at that rate, which is a prediction of a Minkowskian spacetime. So those are two main observations that measure the local symmetry of space and confirm that it is a Minkowskian spacetime with the length to time ratio of c. All right, so once we have a cobordism, our model space is moving along, and the dynamics we observe are waves carried along with it. I note that one explanation that one could have for this is that, well, these are just properties of the wave in the medium, and that is one difference between this and, say, the mechanical universe interpretation. Anyways, so space is moving. All of our observed dynamics are waved, carried along with it, and the speed of these waves may depend on the direction. So if we're in a gravitational well, the speed in the radial direction is going to be different than the speed in the transverse direction, perpendicular, going around the object. And that difference is actually what causes the precession of Mercury. So that difference in direction is an anisotropy in the reference frame. So basically, at each point, there is a field of vectors. There's a time-like vector that represents the velocity of the space-time. And then in the space perpendicular to that, there is a stretching vector that corresponds to how that direction is stretched. And we can change basis to where that stretched is isotropic. And then we can even scale it so that it is a proper Minkowskian reference frame. So what a tetrad field is the basis of an isotropic reference frame co-moving with the ether of the waves moving in the ether. So it's basically the local reference frame of the space-time itself. Now, if we're viewing the rest case as being a Minkowskian reference frame, and then we've distorted it, and then our space-time coordinates are distorted, then basically this F matrix, this tetrad field, is very analogous to the classical deformation gradient of an elastic solid. So it basically corresponds to the differential deformation of the space-time relative to our coordinate system. The deformation of space-time from its rest state as measured in our coordinate system. Okay. So using polar decomposition, we can decompose any matrix into a Lorentz matrix times a symmetric matrix representing the principal axes of distortions. I'm going to call this Lorentz matrix a rotation matrix, even though it includes both boosts and rotations. Once I have a deformation gradient, I can immediately, from teleparallel gravity, define the metric. Well, they would say once I have a tetrad field, that defines the metric. And it's independent of this rotation parameter. So only this symmetric part corresponds to the metric. And in fact, the deformation gradient, and if I were looking at only the three space part, this metric in here would just be the identity matrix. And this tensor, U inverse U, is how we define the classical strain tensor. And the classical result from elastic solids is that strain is independent of rotations, even accumulation of infinitesimal rotations. So it's not a surprise that the metric is independent of the rotations in our space-time, including boosts. Now, we have a metric. We have a space-time. We also have, for mathematics, a Nash embedding theorem, which tells me that I can find a higher dimensional space-time where the metric of our space-time is equivalent to the metric of the embedding. It's an isometric embedding to some higher dimensional space. And one of the issues that I believe that make general relativity hard to explain is that we have spent a lot of time trying to understand these extrinsic dimensions and figure out what does space look like in these higher dimensions to produce the geometries that we have with the isometric embedding. When really we have our celestial reference frame, why not stick with our measurements with that and then realize that this metric can be handled by an intrinsic basis frame to where the waves in our space-time are moving isotropically in a Minkowski reference frame. So why do we need these extrinsic dimensions when an intrinsic basis field is sufficient? So that is why, even if there's no mathematical difference, it may be actually easier to solve equations and models with this viewpoint than with the classical viewpoint, the standard viewpoint from general relativity, rather. And really, the difference is similar to in fluid dynamics. You've got the Eulerian reference frame where you stick to the coordinates and deal with everything relative to a fixed coordinates, which is closer to the approach that I'm presenting here, the teleparallel approach. And then you also have the Lagrangian formulation where you take a co-moving frame from the perspective of a particle co-moving with the fluid and then measure the dynamics relative to that. And that would be closer to the traditional approach to general relativity, where we try to find the actual shape of space in higher dimensions and then do all of the geodesics relative to that higher dimensional space. But we don't need those extra dimensions. We can just have a basis field relative to our medium. All right. So in order to do meaningful physics, we need to be able to take derivatives. And one of the main issues mathematically with derivatives is that partial derivatives are not independent of our parameters. And we like our equations to be independent of our reference frames. our measurement coordinate system that we use to measure. If we rotate the reference frame, if we go from a Euclidean reference frame to a spherical coordinate system, we should expect partial derivatives do not preserve the equations. We need extra terms, and basically a connection describes those extra terms that we need. And then that will produce covariant derivatives. Now, sometimes people talk about torsion and curvature of space-time, but those are not properties of the space itself alone, but only when we have a space and a connection on that space can we meaningful talk about torsion and curvature. Once we have a space-time with a metric, we can define a connection where that torsion that preserves the metric and has zero torsion. And if we have those properties, there's only one metric that has that, and that metric has the name, the Levi-Civita connection. The metric is independent of our rotations. So the metric is also going to be independent of that rotation parameter. And one thing that I didn't understand until studying the mechanical universe is at the teleparallel gravity, they talk a whole lot about the spin connections. And I didn't understand what they were preserving. And it turns out what they're preserving is exactly a rotation field. So if we have, in addition to our metric, we have an additional rotation field, and we wish to preserve that, that's going to introduce what they call a spin connection. The Weizenbach connection, now our deformation gradient has both the symmetric matrix and the rotation matrix with this polar decomposition. So if we have the metric and the rotation, what we're really preserving is a tetrad field or deformation gradient. And using its inverse and derivatives alone, we can define and it's actually, once we have a full matrix that we're needing to preserve, that introduces a Weizenbach connection to preserve that matrix. And because, well, if we preserve the deformation gradient, that's going to preserve the metric. So it's going to be a metric connection, but it is not the Levi-Civita connection. So it is going to introduce torsion. So the torsion is, by definition, for any connection, the difference between these two vectors. If we were flip these last two indices. Now, the Levi-Civita connection is very famously symmetric in these two indices. So then when I subtract those, it does have a torsion tensor. It's just that torsion tensor is identically zero. So when it says torsion free, it doesn't mean there is no torsion. It means that torsion is identical. The torsion exists. It's just identically zero everywhere. One interesting thing about this Weizenbach connection is that when you calculate its curvature tensor, because there's another formula like this, a lot more complicated, to give you the curvature of a connection. And with this Weizenbach connection, it cancels out to be identically zero. So in the teleparallel gravity, we have these Weizenbach connections where gravity is defined in terms of these torsion tensors with zero curvature, whereas the standard general relativity telling, we have a metric alone, and we have this torsion-free Levi-Civita connection. Both can be used to describe gravity, and that's largely because whenever we have two connections, their difference defines another tensor, and when one of those tensors is a Levi-Civita connection, the difference between the new connection and the Levi-Civita connection is called the contortion tensor. And that is basically defined to be the difference between these two tensors. It turns out you can express the contortion tensor in terms of the torsion alone. And what this contortion tensor represents is Snell's law and the material derivative of waves. So the Snell's law represents the changes due to changes in the index of refraction. It could be isotropic. It could be different in different directions. And perhaps as the index of refraction as a whole, that would be in the time-like component changes. Those type of changes due to changes of index of refraction, perhaps different in different directions. That's going to cause the wave to bend, and that is incorporated in Snell's law. And then that gets encoded in the contortion tensor. And also, the material derivative of waves as a wave is moving through our space-time. Well, there's going to be part of the change due to the actual change in the value of that parameter at that point in the wave. And there's other parts as the wave is moving through, it's going to be bringing stuff with it and taking stuff out of it as the wave moves through. And that the material derivative handles those changes from the fact that the wave is flowing through a point. So that the gradients in whatever parameter we're measuring contribute to the change, the observed change in that parameter at that point. All right, so that's connections and derivatives, and actually introduction to torsion. Once we have a torsion tensor, that can be broken up into three principal components. The first part is basically the trace of the torsion, which is the vector torsion. Another part is I can lower one of the components of torsion and then apply the anti-symmetric symbol. And that produces a genuine tensor that is the axial torsion. And then the pure torsion is essentially what's left. If I take the torsion and I subtract out those components, I get a new tensor that when I calculate the vector torsion of that new torsion is 0. And when I calculate the axial torsion of that new tensor, I also get 0. So that gives me a pure tensor part of whatever's left after I take out those first two parts. So vector torsion seems to be what compares most directly with Chantel-Ross mechanical universe model for the electric potential. In particular, if our deformation gradient is static and the index of refraction is constant, then the resulting vector potential of the vector torsion, the vector part of the vector torsion, would be exactly what she is calling a spin vector. If v has a velocity component, that would introduce a vorticity term into our torsion. And it also has terms related to the gradient of the index of refraction. The scalar potential, if I'm taking the vector torsion as the actual electromagnetic potential, the scalar potential would then be very similar to the helicity of the motion. And the scalar potential, basically, charge is just going to be the Laplacian of the scalar potential, which is basically the typical, the variation of that point relative to its neighbors at a particular point is what charge would be. And so basically, conservation of charge would be analogous to the conservation of helicity. And here we're actually talking about distributed in the area. So we're talking about the charge of the field around a particle. So this is more related to the running of the fine structure constant as we go into an electron. The charge of the virtual particles that accumulate around an electron to shield a higher charge in the center of the electron. Anyways, the conservation of charge would be analogous to the conservation of helicity. I don't want to explain that running of the fine structure constant here. I probably shouldn't have brought that up. All right. Axial and pure torsion now remain as, well, the vector torsion is electromagnetism. There's two more components. There's two more forces for quantum dynamics. Maybe they're related. And in particular, the use of the antisymmetric tensor seems to tie the axial torsion much more directly to our spacetime than the others. And so that means, and our space-time is connected to the mass and gravity, so we might expect that one to have the massive bosons of the weak interaction. And also, the strong interaction has a much larger group, so it needs to act on a much larger object, and the pure tensor part seems to be big enough to support the degrees of freedom needed for the strong interaction. And when you look at the weights of these three components in teleparallel gravity to get the total tensor vector, you find that they are remarkably similar to the weights of the Lie algebra of the symmetry group of the standard model described by John Baez that I will link in the description. However, these numbers, being 2, 3, and 6, are small numbers, and so we're kind of running into the strong law of small numbers, which suggests there aren't enough small numbers to meet the many demands of them. So this could be coincidence, probably until somebody shows that it's not coincidence. Probably best to assume it is coincidence, but it's an interesting coincidence. So if I take all of these threads and bring them together into one model, the picture that I get is that our universe has the local structure of a cobordism between two space-like 3 manifolds, and in fact, if we go all the way back, a cobordism between the single point of the Big Bang and the 3D space that we observe today. Time plays the role of the Morse parameter of this cobordism. The motion of space can be specified using a deformation gradient, and technically that is the distortion of space locally from its rest state is what the deformation gradient actually is. The strain of the deformation gradient is what the metric is. That is the nature of the metric. The connection preserving the deformation gradient introduces torsion. This torsion represents the forces of quantum mechanics, electromagnetism, the weak interaction, and the strong force. The Bohmian kernel of particles are local holes in the cobordism. Their discrete values are analogous to the residue theorem. So inside the area, I would expect that the quantities of certain conserved parameters would be preserved inside the area. And then if you have changes happening, they would have to preserve the total sum. And basically using Stokes' theorem, when changes happen, when topological changes happen, that has to be a preserved quantity. They're preserved quantities that still have to be preserved. Anyways, the interactions are the singularities in the Morse function, where the topology changes from the cobordism. So already, this model gives us a better view of quantum interactions. They certainly have a better ontological meaning than interactions are just random things that we can't predict and just kind of happen. We can measure them. We can determine the expected proportions of them, but there's no rhyme or reason to them. They seem to be completely random. This model actually gives a view of what they could be underneath the hood. The metric is tied to the symmetric matrix alone, and the symmetric matrix is tied to the metric, which is where gravity and mass are directly tied to. The torsion is introduced to preserve the rotations, but the symmetric matrix also contributes to torsion. So the question that would be the killer app of this model would be if we could use the contributions of the symmetric tensor to calculate the particle masses from the contributions of the symmetric matrix to torsion. So do those contributions generate the masses that we observe for particles from conditions at the Earth's surface? So that is my Cobordism model, and I think I'm going to go back. I haven't been to CosmoQuest in like 14 years. I think I am going to go back and give a go of defending this model there in the month of June. So hopefully I can see you there. I'll also be looking at the comments here and hopefully get some feedback on this model. And thank you for watching. And if you're interested in this, subscribe. And as I have more developments, I'll bring them here. Although I'm going to be focused more on developing videos for calculus level and below, as I'm thinking about writing a calculus book, although those plans might be not as set as they were a few weeks ago. Anyways, thank you for your time, and I look forward to your input.